So in the previous video, I was actually speaking to myself for a second. It was kind of weird because the computer stopped filming when I was explaining this example. So I will briefly give you a summary of what I did, and then I'm gonna solve the last problem. So in this case, we have, as explained in the last minutes of the previous video. So we have now a similar situation, but in this case we are going to have two areas enclosed together. So in this case we want to maximize the area, which is xy, and in this case the constraint will come from the total amount of fencing, but in this case they are not giving us the constraint in the form of an equation. So in this case we have to figure that out. So let me erase this so it doesn't make anything unclear. And then, so in this case, I'm going to have x plus x plus x, which is 3x's plus 1y equals 6,000, which in the form of a constraint g of xy is going to be this whole thing right there. That is going to be in the Lagrangian function. And then from here, you would go the same way as we did in the previous example. Now for the word problem below, we're going to have a company that has two plants, one in San Diego and the other one in LA. So the firm is committed to produce a total of 169 units of a product each week. The total weekly cost is given by this function. So in this case, X represents the number of units produced in San Diego, while Y represents the number of units produced in LA. How many units should be produced in each plant to minimize the total weekly cost? Okay, so from the sentence I highlighted, I'm going to obtain the constraint equation. In this case, one thing to keep in mind, well, the word total is going to tell us what operation to use. So the total from San Diego and LA, which is x and y respectively, add these two letters, x plus y, should be equals to 169. And writing this in terms of constraint, this will be our g of x. So in this case, the Lagrangian, well, if you will, this is f of xy or c of xy. In this case, they use the letter c to xy plus lambda times g of xy. This is how we will form the Lagrangian function. And then, of course, from there, take the corresponding partial derivatives, combine the equations to find x and y. Now, the reason why I'm helping you setting a problem like this is because in the homework, you will see at least one of these problems, one of the problems that look like this. All right. So the next and last thing I want to cover about Lagrange multipliers is how to solve a problem involving three variables in this case. It's going to be a very interesting, it's going to be a lot of fun to look at a problem like this. So let me have my notes here together. All right. So we use Lagrange multipliers to minimize a function f of x, y, z equals to xy plus xyz plus xz, subject to the constraint xyz equals 12,000. All right, so this one, take a deep breath because this one is going to take a good minute to solve. Now, let's first of all write this in the form of a constraint xyz minus 12,000 equals to 0, in which this is g of x y. Okay, so let's see. Let's form the Lagrangian. The Lagrangian will look a little bit bigger in terms of notation. X, Y, Z, lambda equals to the objective function, which is f of x, y, z, plus lambda g of x, y, z. By the way, I forgot a z right here because z is variable, not a constant. So, comma, z. And then I'm going to have the all this over there. Okay? So, lambda of x, y, z. I mean, L of x, y, z lambda. That's not lambda again. That's 2x y plus 6y z plus 8x z plus lambda times, well, not g actually, what am I doing here? And times x, y, z minus 12,000. So in this case, what are we going to do? We are going to take 4 partial derivatives. So in this case, the procedure described in the second page, in which we combine this and that equation, it's not going to work exactly. So because in this case, we're going to have more equations, more variables, and we are going to combine the equations in a different ways. But still, lambda, I mean the partial derivative of the Lagrangian with respect x, the partial derivative of the Lagrangian with respect y, the partial derivative of the Lagrangian with respect z, and the partial derivative of the Lagrangian with respect lambda. So let's give this system of equations notation, and let's find the 4 partial derivatives. So the partial derivative with respect x, in this case it's going to be 2y, 2y, and 0 and 8z. Plus the derivative of x, y, z with respect x is going to be yz, because those are constants, times lambda. So this will be plus lambda y z. And then for the partial derivative with respect to y, this is going to be 2x and 6z plus the derivative with respect y is going to be xz times lambda. Next, the derivative with respect to z. This is going to go with 0, 6y plus 8x and xy times lambda. And finally, the partial derivative of the Lagrangian with respect to lambda will be no other than the constraint here, x, y, z minus lambda. Minus actually 12,000, not lambda. Alright, so how are we even going to solve? Because look at this. We have more variables, we have more equations. So this is what we're going to do. First of all, I'm going to write x, y, the equations 1, 2, and 3. I'm going to write them in a different form. So, by the way, this is equal to 0, equal to 0. Oh, come on. I'm making a mess here. Oops, I'm making a mess here. I'm going to fix this mess. Equals to 0, equals 0, equals 0, equals 0. So let me call this 1, 2, 3, and 4. So I'm going to solve for this term, for the term that has the lambda. So in this case, lambda y z equals, well, actually, let me do that below. Okay, I'm going to write the whole thing. 2y plus 8z plus lambda y z equals the 0. And I'm going to move these terms to the other side. Lambda y z equals negative 2y minus 8z. And then to get lambda by itself, I'm going to divide both sides by yz. Okay, so I'm going to divide both sides by yz to get lambda equals, I'm going to factor out this negative sign. That's going to be 2y plus 8z divided by yz. Next, I'm going to do the same with the second equation. 2x plus 6z plus lambda xz equals to 0. And I'm going to have lambda xz equals to negative 2x minus 6z, and lambda xz equals to negative, I'm going to factor that out, 2x plus 6z over xz. Again, what am I doing here? Divide both sides by xz. And then I'm going to divide finally by x. Wait a minute. What am I doing here? I'm dividing by xz here. Never mind. Okay. Wait a minute. No. Forget about this. xz. Okay. We're good here. I'm going to do the same to the third equation. 6y plus 8x plus lambda xy equals to 0. So I'm going to solve for lambda xy. That equals negative 6y minus 8x. And then I'm going to divide both sides by xy. And at the same time, I'm going to factor out this negative sign. This goes in the front rather. So what we are redefining equations, or the one I was supposed to erase is also this xz. So I have new redefined equations 1. I'm going to use a different color, in fact, to label them. Equation 1, equation 2, and equation 3. So how am I going to solve this equation? All right. So in this case, first of all, I'm going to combine 1 and 2. Combine 1 and 2. So combining 1 and 2, I will have, I will set equals. If lambda equals lambda, well, we can set these two expressions together. But notice how I can at the same time eliminate the negative signs. Because negative and negative, well, if you will, they turn into positive, or we can just erase those. Okay. Now, how am I going to solve this equation, and how? So I'm going to solve this equation for x, and I'm going to leave it in terms of y. At the end, I'm going to explain why did I choose to do that, and what alternatives are there to solve this problem. Okay, so in this case, I don't want these denominators. So what I will do, I will multiply both sides of this equation by the LCD. In this case, the LCD is going to be the product x, y, z, x, y, z. So when I distribute this, notice how the y, z's divide out, and in this case, the x and the c's, the x's and the z's divide out. So I'm gonna get here x times 2y plus 8z equals to y times 2x plus 6z. So now that we got rid of those denominators, I'm going to distribute to have 2xy plus 8x z equals to 2xy plus 6yz. Yes, a lot of terms, a lot of variables, but something really interesting that's going to happen here. 2xy on both sides, they're going to go away. And then we are going to get 8x z equals 6yz. And in this case, notice how we can cancel out the z's as well, leaving us with 8x equals 6y. So x equals, dividing both sides by 8, we get 3/4 of y. I'm gonna explain why am I writing x in terms of y, and for the next combination I'm going to do the same. I'm going to combine 2 with 3 this time. So combine 2 and 3 and write. So here we wrote x in terms of y. And in this case, I'm going to write z in terms of y. So whatever we do in these two combinations, we solve for one letter and the other, but we need to write them in terms of the exact same variable in order for this to work. So I'm gonna leave it this way over here so you can see the whole thing. So let me put a bar over here. So I'm going to combine negative 2x plus 6z divided by x. Z equals to, what is this going to be? Negative 6y plus 8x over x, y. Again, negative and negative become positive, or we can simply erase this. So now I'm going to multiply both sides of this equation by the least common denominator in order to get the denominators canceled. In this case, again, is xy, z, xy, z. And then when we distribute this x, y, z, notice how the x's and the z's go away, leaving us with y times 2x plus 6z, essentially the same as we did before. Equals over here, the x's and the y's go away, leaving us with the z. Which is in this case 2xy plus 6yz equals 6yz plus 8xz. All right. Do we have any common terms to cancel out? Of course, 6yz with 6yz. And then 2xy equals to 8xz. Notice again we can divide out the x's. So we get, in this case I'm gonna write the reversed equation, 8z equals to y, because all I want now is to solve for z, which is gonna be z equals to 1/4 of y. So we have, in this case, instead of having two quantities, two numbers like we did with the other types of systems of equations, we're getting two variables in terms of the same x and y. Why are we going to do that? Because we are going to go back to our constraint, sorry. I'm going to write x whatever I have in terms of y, and this c whatever I had in terms of y, because I already had a y over here. So what's the alternative way? The alternative way is to solve for another variable. For example, I could have solved for x. I could have solved for y in terms of x or z in terms of x, but in this case there's no way to get z in terms of x, so that's why we write everything in terms of y. So let me go ahead and do this. What is this? X, y, z equals 12,000. So in this case, x in terms of y, it's going to give us 3/4 of y times the y that it's already there, and z, which is 1/4 y equals 12,000. So y times y times y will be y cubed, and 3 times 1, which is 3, over 4 times 4, which is 16, equals 12,000. Okay, and then when I simplify this, I'm going to multiply both sides by 16 and then divide by 3, or multiply by the reciprocal, 16 over 3 times 16 over 3, and then this is going to yield the following: y cubed equals 64,000. And if we take the cube root, this will be y equals 40. Okay, so now that we have y equals to 40, we can use these two equations to find x and y. I'm gonna do that over here. So I'm gonna use this box over here. So x equals 3/4 of 40, and z equals 1/4 of 40. Now 40 divided by 4 is 10 times 3x equals 10, and 40 divided by 4 is 30. 40 divided by 4 is 10 times 3 is 30, and 10 over here. So now we have the critical point, finally, after solving equations in many different ways. Okay, so I'm going to go up here to the original function, and I'm going to call this our critical point. The critical point will be x equals 30, y equals 40, and z equals 10. Okay, so I'm going to plug in this over here. 30 where corresponds to x, 40 for y, and 10 for z. So I'm going to do that over here. I'm going to use this space. So 2 times x, which is 30 times y, which is 40, plus 6 times y, which is 40, times z, which is 10, plus 8 times x, which is 30, times z, which is 10. And if you use a calculator for all this, you will get that the maximum value for this function is 72,000. So this is one example of applying Lagrange multipliers to functions that have, in this case, 3 variables as opposed to the previous ones in which we deal with functions with only 2 variables. Right, so this is the end of this section. I'll see you in the next video.